Welcome back to AI Paper Podcasts. If you're working in AI or robotics right now, you know the feeling. Just this massive overload of information.
Oh, yeah. We're talking, over 10,000 technical papers coming out every year in just the core areas?
It's wild. You just can't keep up, and forget about spotting those really interesting connections between fields.
Exactly. So today we're diving into a paper that tries to tackle this exact chaos. It's called Real Deep Research, or RDR for short.
RDR. Okay, so what's the core idea? How does it help?
Well, basically, RDR is this automated pipeline. It uses large language models, LLMs, and the whole point is to act like a research analyst for you, one that's, always up to date.
An always-on research analyst. I like the sound of that. It takes that huge pile of papers and makes sense of it.
Precisely.
Yeah.
Turns it into a structured, kind of actionable map of what's actually happening in the research world. For technical folks like you listening, this could be a real game changer.
Okay, let's jump straight into the highlights then, maybe for folks catching the short version. What are the key takeaways from RDR?
Right, first up, visualization. RDR actually maps out the entire research landscape. Imagine papers as little dots, right? And related topics. They cluster together, forming these visible spheres on the map. So you can literally see the structure of the field.
Okay, visualizing the landscape. What else?
Well, that map immediately shows you momentum. RDR found, for example, a really steep rise in interest around teleoperation, dexterous manipulation.
Stuff involving robots interacting with the world more finely.
Exactly. And also, interestingly, a big jump in low-cost open-source robotics hardware and software. That's a big trend.
And does it show things slowing down, too?
Yeah, it does. It suggests some areas, like maybe traditional reinforcement learning, some specific types of skill-based manipulation might be hitting a bit of a maturity curve. The growth isn't quite as explosive, maybe.
Interesting. So it's not just finding what's hot, but also how hot, relatively speaking. You mentioned structure earlier.
Ah, yes, the structure. This is crucial. RDR doesn't just give you a fluffy summary. It forces the LLM to analyze each paper based on specific things defined by experts.
Like what kind of things?
So for a robotics paper, it might look at the exact input sensors used. Or for a foundation model paper, maybe the specific objective function it's trying to optimize. It's very granular.
Okay, that makes sense. Structure matters.
And it pays off. They did tests. RDR's generated summaries, these domain-specific surveys. They got an average rank of 1.30. That significantly beat commercial LLMs like GPT-5, especially on these really technical tasks.
Wow, 1.30 is a strong rank in pairwise, so the structure really helps avoid nonsense.
Basically, yeah. It proves that this structured, embedding-based approach has real value for digging into the details.
Okay, so that's our mission for this session. Really unpack this RDR pipeline. We want to see how they're using semantics, embeddings, all the good stuff to cut through the noise for researchers.
Let's do it.
So, starting with the motivation, we know the volume is insane, exponential growth. But what's wrong with the old way? Traditional expert surveys.
Well, the big things are time and scope. I mean, a human-written survey takes months, right? By the time it's out, especially in AI, parts of it are already, maybe a bit dated.
Yeah, the field moves too fast.
Exactly. And maybe even more critical is the scope problem. Experts tend to stay in their lane. A computer vision expert might write a great CV survey, but they might totally miss a breakthrough in, say, NLP embeddings that could actually revolutionize their own work.
Ah, the cross-domain blind spots. That's a huge issue.
Huge. And RDR is designed specifically to try and bridge those gaps.
So how does it do that? The paper mentions 4 main capabilities, right? It sounds pretty comprehensive.
It is. First, it generates those detailed surveys we talked about, but tailored to very specific research questions. What a technical user actually needs.
Okay, specific surveys. What else?
Second, the trend analysis. Seeing what's heating up, what's cooling down, real-time momentum. Third, mapping those interdisciplinary connections. Spotting the cross-domain opportunity.
Force.
Retrieval. Basically, semantic search. Once you know a topic is interesting, you can use RDR to pull up the most relevant, high-impact papers for that specific query.
That all sounds
Yeah.
Incredibly useful. And is the pipeline itself general? Could you apply this outside AI?
Absolutely. The framework is designed to be generalizable. It's 4 main steps: data preparation, content reasoning, content projection, and embedding analysis. You could point this at almost any research field.
Okay, let's walk through those. Data prep first. Garbage in, garbage out, right?
Yeah.
So what's the input data look like? Needs to be fresh?
Totally. They're crawling papers systematically from all the top-tier places researchers care about: CVPR, NeurIPS, CoreRL, RSS, ECCV, ICLR.
The big conferences.
The big ones, yeah. Plus, they pull from key industry labs, NVIDIA, Meta, OpenAI, Google DeepMind likely too, places publishing influential work.
And how recent is it? You need very current data for trends.
Crucial point. For this analysis, they specifically filter down to papers published from 2024 onwards. That gave them a corpus of something like 4,424 foundation model papers and 11,186 robotics papers.
Wow. Okay. Just from 2024 onwards, that's a lot.
It is, but it's what you need to capture the absolute cutting edge, the latest shifts.
All right. Data prep done. Now, the core, content reasoning. You said this is where they make the LLMs act like domain experts, imposing structure. How does that work mechanically?
They actually use a couple different LLMs. For faster, high throughput stuff, like maybe initial filtering, they might use an efficient model. The paper mentions Dubao. But for the really deep classification, the core reasoning, they use a more powerful model. They mention O3.
Okay, different tools for different jobs.
Right. And the key isn't just which model, but how they prompt it. It's not just summarize this. They give it a strict template. The model must classify the paper according to these predefined expert design dimensions.
So they're basically injecting domain knowledge into the prompting strategy.
Exactly. Embedding expertise right into the analysis pipeline.
Let's break down those dimensions. They're different for foundation models in robotics, right? For foundation models, it's IMOWR.
Correct. I is input. And it's specific, not just images, but how the data comes in. Raw RGB, diff maps, video, point clouds, and crucially, the tokenization. Is it using something standard or maybe like diffusion noise as input?
Got it. So very precise on the input side.
M is modeling, the core engine, what's doing the work, attention mechanisms, feed-forward networks, specific transformer blocks like QKV that pins down the architecture.
Oh, must be output then.
Yep. What does the model produce? Text probabilities, photorealistic images, segmentation masks, maybe control signals for a robot. Tells you the model's direct purpose.
W is objective, the loss function, essentially.
Kind of, yeah. But broader. The learning constraints. Is it maximizing a reward? Using contrastive learning. Predicting noise like in diffusion models. It captures the goal of the training.
And finally, our
R is the recipe. How did they actually train and tune this thing? Was it adapter tuning? Instruction fine-tuning with retrieval. Specific pre-training methods. It's the practical how-to.
Okay, IMOWR. That paints a really detailed picture of a foundation model paper. It's like a structured fingerprint.
That's a great way to put it, a machine-readable technical profile.
Now let's switch to robotics, dealing with the physical world. 5 perspectives here too. S, B, J, A, E. What's S?
S is input sensor, the hardware eyes and ears, RGBD cameras, LiDAR, force torque sensors, maybe those newer vision-based tactile sensors, tells you how the robot perceives the world.
B must be the robot itself, the physical body.
Exactly. What's the physical platform? A standard industrial arm like a 6 or 7 OF, a Franca-type research arm, a quadruped, a humanoid, a drone. This sets the physical constraints.
Okay, A is action space, what the robot can do.
Right, and this is critical. Is it low-level continuous control, like setting specific joint torques or a steering angle? Or is it high-level discrete skills, like pick up the block or navigate to point X? Big difference in complexity.
What about J? The outline mentions joint output. How's that different from action space?
Good question. J focuses on the resulting mechanical movement from the motor commands. So even if the action space A is high level, like grasp, the joint output, J, would describe the low-level joint trajectories or forces used to achieve that grasp. It connects the policy to the physical execution.
Okay, bridging the gap. Makes sense. And E?
E is the environment. Where is this happening? Complex real-world driving in cities. A simple tabletop setup in a lab or maybe a standard simulation environment like Mujoko sets the context for the task's difficulty.
S, B, J, A, E for robotics. Again, super detailed. So RDR generates these structured descriptions, thousands of them, but that's still text. How do you get the cool visualization, the map? That's content projection.
Right. This is where the embeddings come in. They take these structured, perspective-aware descriptions, which are already packed with technical meaning, and feed them into a powerful embedding model. The paper mentions using NVIDIA NV Embed V2.
And because the input text is already structured and meaningful?
Exactly. The embedding model can create a much more accurate representation in vector space. Papers that are genuinely similar in their technical approach end up closer together geometrically. It's not just matching keywords in an abstract. It's matching the core technical profile.
So the structure cleans up the signal before embedding. That makes the resulting knowledge graph much more reliable.
Precisely. It leads to much better clustering. You can group papers that share the same I, M, O, W, R, R, S, B, J, A, E characteristics, and that allows the system to automatically generate those concise, accurate key phrase summaries for each cluster.
Okay, the mechanics are clearer now. Let's go back to the insights, the trend analysis. You mentioned traditional RL might be maturing, momentum slowing. What does it practically mean for a researcher? Should they avoid RL?
Oh, not necessarily avoid it. Slowing momentum just means the rate of growth in publications or new techniques in that specific cluster seems to be leveling off compared to others. It suggests maybe the core ideas are well understood. Or perhaps the really rapid progress is now happening where RL is applied to new problems, like using it with these low-cost open-source robots we mentioned earlier.
So it's a signal about where the next big exponential jump might be less likely to occur within that established cluster.
Exactly. It helps you allocate your focus. It's strategic information.
And the knowledge graph itself, the spheres and connections, you talked about the center versus the periphery being important.
Absolutely critical. Those nodes out on the edges, the periphery, they represent niche topics. Maybe a very specific sensor application or a unique math technique. Still important, potentially high risk, high reward, but isolated for now.
But the action is in the middle.
The dense center. Yeah, that's where the magic is happening. That's where ideas from different fields, computer vision, NLP, robotics, core ML, are really starting to merge and build on each other.
So RDR basically gives you a map showing where the research community is already finding these fruitful cross-domain connections.
It's an atlas of where the breakthroughs are brewing right now. It shows you the convergence points.
Now, RDR didn't just claim this works. They tested it. The user study with pairwise comparisons. How exactly did they set that up?
They got experienced researchers, people who know these fields, and showed them pairs of survey summaries for specific technical topics. One summary was generated by RDR, the other by a baseline, like GPT-5 or Gemini.
And the researchers just picked which one was better.
Pretty much. They evaluated based on accuracy, completeness, technical nuance. Does it sound like it actually understands the research? And RDR came out clearly on top, with that average rank of 1.30 we mentioned.
You said the structure helps combat hallucination or errors common with LLMs. How does that work again?
Well, think about it. RDR isn't just riffing on a broad prompt like summarize research on dexterous manipulation. It's synthesizing information from those structured classifications it already made, the S, B, J, A, E profiles for the relevant papers.
So the summary generation is constrained by the prior analysis step.
Exactly. It has guardrails based on the structured data. This makes it much harder for the model to just invent things or make connections that aren't technically sound.
And that really showed up in the results for nuanced topics.
Definitely. The win rates were highest where deep understanding matters most. Like for analyzing the nuances of foundation model output types, RDR won almost 95% of the comparisons. For robotic sensor details, over 91%.
That's convincing. It shows that for really technical summaries, structure beats just raw prompting power.
It seems so, yeah. The domain expertise encoded in the perspectives makes a big difference.
So let's make this practical for someone listening. Say I'm a researcher. RDR tells me dexterous manipulation is hot. How do I use it to find the key papers, not just wade through hundreds?
That's the retrieval capability. Because all the papers are embedded in that rich semantic space, you can query it with very specific, nuanced questions, not just keywords.
Like what kind of query?
Something like, show me papers on dexterous manipulation that use generated data from 3D simulations. Because the embeddings capture the IMOWR or SBJAE info, RDR can find papers that match conceptually, not just textually.
And it pulls up the relevant CoreLL or RSS papers, the high-impact ones?
Exactly. It cuts right through the noise to the papers you likely need to read first. It gives you a high-quality starting point.
Okay, let's try and synthesize this. RDR isn't just using LLMs for research tasks.
No, it's much more fundamental.
Yeah.
It's using LLMs to impose structure on the research landscape itself. It takes that messy, overwhelming flow of papers, applies ESPER-defined perspectives using LLM reasoning, and then uses embeddings to project that structured information into a clear, navigable map, a knowledge manifold. It transforms the chaos.
So for you, the researcher listening, RDR offers a kind of guide. It flags momentum, shows where fields are converging, and helps you pinpoint the most important papers to focus your limited time on.
It's about making informed decisions about where to invest your research energy, finding the gaps, finding the opportunities.
We talked about the dense center of the knowledge graph being where the action is now, these convergence points. But that also means those areas might get crowded fast.
That's a fair point.
So the final thought we want to leave you with, thinking about where the next convergence might happen, look at the edges of the current maps, the periphery. Maybe take a niche sensor from the robotics map, like those vision-based tactile sensors, or perhaps a unique learning objective from the foundation model map, something currently isolated.
Okay.
Where could those intersect next year? Which two currently separate dots on the edge of the RDR map might merge to form the next big high-impact cluster right in the center? That's the discovery space RDR is opening up.
Finding the next center. That's a fascinating challenge.
Something to think about as you navigate your own research path.